So let's start looking at the types of joins. Fundamentally, there are three options for executing joins physically. One is what's called as nested loops. The second is merge join, and the third is what's called as a hash join. The word hash actually has the same connotation as the hash table, hash function that we looked at as part of week one. So if you remember the duality of sorting and hashing, that hashing is what I'm referring to here. In fact, the merge actually has the same connotation as the sorting that we saw, the duality of sorting and hashing in week one. Yeah, so here's another way it manifests, right? Multiple different approaches to do the same thing, to achieve the same functionality, but they have different characteristics in terms of performance. Okay, let's take a look at what these fundamental types are. First is nested loops. As the name suggests, this starts with a loop inside a loop, which takes a look at merging the data elements together. So let's just consider two table joins for now, not extend that beyond. So I have table A, table B. I want to join them on a column K, which is common. And then once I join, I want to do something, right? Doing something meaning the operations that happen further up in the relational algebra tree. I want to execute all of that once the joins are done, once the joins have been computed. So in physically doing this step of join, effectively using nested loops, I do two loops, one within the other. In the outer for loop, what I do is just iterate over all the records in table A. In the inner for loop, iterate over all the records in table B, and then I go through for each such record. What is the match? If there is a match, we'll do something. If there is no match, then the join actually is yielding nothing. And then, so I keep looping through the inner table records, and then once the inner for is done, the outer for loop continues. The ordering of table A, table B doesn't matter. So the nested loop is actually like an associative operation. Commutative operation. It doesn't matter what the ordering is. The performance of this kind of join is going to be the same with respect of the ordering of the tables here. So it's going to be n times n. If you have n records in A, n records in B, n times n is what you need in terms of the time it takes for us to go through this kind of a process. The other angle here is for you to be able to iterate over all the records of one table while the other iterator is also live is the assumption that both the tables have data which is small enough to fit in memory. So that's a pretty big assumption. Keep that in mind. Merge join, on the other hand, is a slightly more sophisticated example of physically executing a join. So here, I want to look at the join operation itself as an interleaving or merging of two different streams of data, where the streams are written sorted, such that I don't have to look at too many elements of data at the same time. I just have to look at within a neighborhood of data values which are potentially going to match with what I have today, like what I have at the particular point in time. So the way I go about physically, executing this is first up, just sort the tables respectively, not together obviously, but respectively. And once you sort the tables respectively, then you pick up like an iterator over the sorted tables records of each. So in this case, iterator I over sorted table A's records, iterator J over table B's records, and then you look at whether the keys match. Because the keys are drawn from the same domain, you would expect the values to match or not match or be greater or be lesser. There needs to be some very clearly defined comparator, right? That should be possible on the key data type. So you could just have different if conditions for each of the different values of the comparator. So the first is the two values match, right? In which case, that's exactly what you want as a join. So do that something that you need functionally, that you'll be done. Once you're done, then you just iterate. You increment um, the record, the iterator to the next record in table B. That way, you're moving the neighborhood a little bit while maintaining the table A's iterator as it is. So that way, you're only joining local portions of the data, not worrying about the whole grand thing. If J's key, on the other hand, is greater, um, comparatively speaking, then it means that the neighborhood of records in B has already moved on to the next key. That's what this means. So therefore, you have to shift the neighborhood of records of table A. So that's why you come back and increment I and then start the entire thing again, right? And vice versa. If I is actually moved on, J is actually at an earlier key, then you increment J and then start the entire check. So this way, the comparator is always applicable only to a local neighborhood, like I mentioned. So you don't have to worry about the entire grand join that you need to perform. But this is possible only if the data is actually ordered based on the key. So the sorting is a critical prerequisite for this join to work. The third type of join is a hash join. So here I'm going to just take one of the tables, let's say table A, and look at the key K, which means the column K. I look at all the values of column K and I hash it. Right? When I hash it, I get basically a hashed output. The hashed output becomes a key in a key value store, for instance, a hash map in a Java collection, as an example, right? Or it could be some other hash implementation, doesn't matter. But you'll have a table like this, and in that table, the key, or rather the hashed value of the key, is what is getting indexed on, and then the values that you need. And usually, you would need all the different columns of table A necessary for operations that happen higher up in the relational algebra tree. All of those values for that record to be available here. And if there are multiple records, then you will have like an array of those or list of those records, right? So that's what gets created as part of this hash table. So effectively, you've taken that table A, which is laid out in a matrix, right, rows and columns, and you've taken that into a hashed list representation, where the hashing is on the key. The index is actually basically the hashed value of the key. The value is actually a list. The list is a bunch of records, all of which have the same key, same value of the key, right, in table A. So that's how you can mentally map this. The advantage of this structure is that now when table B gets passed or read, I can just look at each record of B, not have to worry about whether table B is sorted or not have to look through all the records of B for all the records of A. I can just do this individually. So basically, I look at for each record of B, compute the same hash function. That will give me an index into one of these values. If I don't find any such indexed value already available, it means that this particular value of K in table B does not have a matching record, which means there is no join. Right? Likewise, if I have values in table A for column key, for the key column K, and there is no such value in in column K in table B, you will never find any instance of this operation which will pick up a specific entry, right? Because you're iterating on the record of table B, not on the set of all possible keys anyway. So that's how the non-join operation is avoided. The join operation, on the other hand, is when the hash actually picks up a value that already exists, and then because you're operating on one record, that record is merged along with the list of records which are stored here from table A, which have the same value, and then you do something about those merged records, right? Um, and you work it out the final answer based on the relational algebra tree. That's how you get the join executed. As you can see, these are three different foundational um, join types. It's fundamental because all the other variants are trading off or picking up from these three, like or one or more of these three, and they then build their own variant. Right? That's how they vary. But yeah, if you understand these three, then this becomes easier to understand how do big data joins happen. So let's just look at a brief commentary on the performance characteristics of these three. So the nested loops method is fundamentally going to be useful only if the records of a table A and records of table B all fit in memory. If that does not happen, then the ability for you to do like an inner loop and an outer loop will become extremely expensive because you will have to constantly keep looking up the disk. Due to not having enough memory, the program will do what's called as crashing, meaning the data is actually not in the cache in the operating system. And the data also has, excuse me, yeah, and the data also has too much of back and forth from memory to disk, and that affects the performance characteristics as well. So that is what will cause a lot of problems in terms of performance. So this means effectively that for nested loops to work, the data sets A and B should be small enough to fit in memory. Then, in which case, we can just breeze through just within the at CPU speed. Effectively. By the way, the algorithmic complexity, right, notions of the algorithmic complexity, the time it takes to execute an operation, etc. All of that theoretical analysis is applicable only if the data fits in memory. So for this nested loops kind of an approach, you're going to have like an order n square, assuming n is the rough order of magnitude of size of data for both A and B. For a hash join, on the other hand, you would have a very different memory profile. Here, first and foremost, notice that you're going to use this only if the data sets A and B are not small enough to fit in memory, which means at least one is large. If one is large, what can you assume over the other? I'm going to assume that the keys are not that many in number, which means the domain of the join is actually small enough to fit in memory. So again, notice what I'm saying here. I'm not saying the entire table fits in memory. I'm saying that the set of keys which are possible, or the set of keys which are actually present in table A, that unique set of keys that fits in memory, right? Even though the list of records which belong to which have the same key is something that I was logically talking as though it's stored in that structure in a hash table or a hash map. In reality, that's not how it happens, right? The list is not like a in-memory copy of the data. It's actually in some cases just like a point to look up to like some other place where it's actually already stored. So those are specifics of the implementation. But in effect, you would need the table A's keys to fit in memory because that's how the hash is constructed. And once that's constructed, B can be large, B can be extremely large, doesn't matter. You're just looking at record by record of B. You're not really doing anything else on the data set of B. So in this case, already you start to see that for big data purposes, the hash join is likely to be your friend to do a join as opposed to a nested loops method. What about merge join? So here, the fundamental characteristic is that you're not making any assumptions about what fits in memory at all. Why? Because if you remember the way the algorithm itself is set up, I'm looking for each of the tables. I'm looking within a neighborhood, local neighborhood of the key for matches with the other local neighborhood of the other table. Right? It's not a grand operation that looks at the entire thing. So in that kind of a setup, I don't need all of that to be stored in memory. Right? I just need the local neighborhood to be available to me. But to arrive at a contiguous way of creating the local neighborhood, I do need to do the sorting. But the sorting again is on individual tables. I'm not joining both tables or I'm not merging the tables and then sorting it. The sorting is happening individually. And that sort by itself could be doing a merge sort because the tables could be large, right? Doesn't matter. So it's a very, very scalable operation. It scales gracefully with the increase in data sizes. As opposed to a hash join scales well in terms of dataset B, but as dataset A becomes larger and larger, and the domain of keys becomes larger and larger, at some point the hash joining method will just start crashing also because it doesn't have enough memory to fit all the different keys. So the operating system will start to evict certain portions of the hash table and that throws performance out of whack. And then nested loops is like the least efficient in terms of large data sets. In fact, it may not even work. Okay, so those are the three foundational types of joins. Let's build on these, right, with variants which are specific to big data. So there are two variants which we should be aware of. So first and foremost, merge join and hash join do the same thing. That comes from the duality of sort and hash. Merge join is most scalable. Like I said, it just looks like neighborhood at the time. And what this means is also that it's the least efficient in terms of time taken to do the join if other options are possible. So the way the optimizer in a SQL context would end up looking at this decision is to say, do I know enough about the data to choose nested loops because that's the fastest? If not, can I safely assume that it can be done using a hash join and not have to worry about crashing? Or do I have to compulsorily end up choosing merge because the data sets are just too large? So that's the decision flowchart if you think about it. Effectively, within hash join itself, there are two variants which are possible. One is called the partitioned hash join, the other is the broadcast hash join. In a partitioned hash join, especially when the tables are large in size, you could look at the tables being large in size in two ways. First is the table A on which you're building the hash function. That itself is having a domain of keys which is really, really big and doesn't fit in memory of any single machine. In which case, you can partition that table and effectively you're partitioning the key space into distinct chunks. And then you're joining only within those chunks. So remember I was saying the variants just play on each other with respect to having picking up the best parts of different join types. So effectively, the analogy here is the local neighborhood join that's happening in merge join, right? I'm trying to mimic that same operation here, but have a very strongly defined notion of what a neighborhood is. In this case, it's a partition, and the partition is effectively a distinct key value of a key, a distinct list of values for the key. So, in doing that, even if the entire domain of AS keys is very large and doesn't fit in memory in a single machine, I'm only needing to worry about a distinct set of values which partition the bigger range, right? A bigger domain rather. So in which case, I just pick up that partition, but then what aspect of B do I pick up? The classic hash join doesn't make any assumption about the size of B. B can be as large as possible. I'm just going to do record by record check, right? But if I do this partitioned ways of looking at the key, And if I don't make a special assumption about B, I might end up reading all of B for each of the number of partitions that I created for column K, right? And that will be really, really wasteful because B is large. So what you then do is you partition B as well. So this way, you take A, you take B, you say pick up the column K for the column I want to join on, and then partition in the same way using the same hash function, such that the set of values that have the that actually hash to the same worker or same execution for both A and B are the same. So you're gonna have a very high chance that the values match. And once the values match, that's your neighborhood that you need to search in. You don't need to worry about the rest of the neighborhoods which don't match. So that's how I separate the join problem of those two big tables to multiple join problems of smaller tables, basically subsets of the bigger tables. That's how this works out. And then the multiple smaller joins can operate in parallel because you have access to this cluster of machines. So that's the partitioned hash join approach. The other option here is what's called as the broadcast hash join. So here it really is a nifty trick which allows you to execute on a hash join much faster than any of the other types under a specific situation, which is B is large, like we spoke about, but also that A is small, right? So if A is small and B is large, obviously you can use nested loops, B is large, right? Merge join is too inefficient for this kind of a setup. You have an easier and a better way to do it, which is you take A and you create a copy of it in every single execution environment of B. Meaning, if B is already large, which means it's already spread out across multiple executions or executors in the world of Spark, multiple worker nodes in the world of Hadoop, right? So that's why I'm referring to it as part of B. I'm not consciously calling it as partition. I don't want the partition B. B can be as it is, doesn't have to change. So B is already spread out across multiple machines in the cluster. So to each of those machines where B is present, just send a copy of A, an entire copy of A. You don't need to partition A, right? That way, the B part that exists in a certain machine can have representations of keys from the entire domain, right? Or maybe some subsets of the domain. Doesn't matter. Because the A table is copied over in its entirety, the join can be completely locally achieved for that part of B to get to the final answer, which is applicable for that part of B. It's still not the final answer for the entire step, right? It's just a partial answer. And because I'm doing this in parallel, meaning the copy of A is actually made available in this machine, and all the machines in the cluster where B is present. And then the join happens locally. And the join that happens locally can be just a very simple hash join, right? Because A is still going to be a small table. So I just do like a hash table of A and then stream through like that part of B locally in each machine without having to worry about the size of B. That way, I get all the partial answers and then I concatenate and get the final answer. So this way of doing achieving the join is actually much faster than even doing partition join if A is a small table. Alright, so let's just summarize the performance characteristics of these two variants. Partition hash table means I'm partitioning both the tables on the same key using the same function, which means that I'm potentially having to reshuffle data. Why is that the case? Because the way the data is laid out originally may not be partitioned on the same key, right? On the key on which I'm joining, it could be partitioned on something else or be randomly distributed. In which case, when I do the shuffle, when I do the partitioning, I'm effectively taking data and laying it out such that all the records which are the same value for the K occur together. So therefore the shuffle is required. And shuffle, like we spoke about in one of the earlier classes, requires data to be transferred over the network. That could be problematic if the size of A and B are large, even if the size of one of them is large. The broadcast hash join, on the other hand, the only shuffle it requires is the extent of copying table A to every single machine in the cluster. Now, if the number of machines in the cluster is large, let's say 1,000, 10,000 as an example, even though the table A is small, in creating copies, I could be generating artificially a lot of data, but that's all right because I don't really need uh, that data to be persisted beyond the lifetime of the join. I could just throw away right once the join is done. It still might be actually cheaper than having to partition B as well, right? Because in this broadcast hash join method, I'm completely avoiding the need to shuffle B across. And the only dependency on B is just reading every record of B once. No sorting required, no shuffle required. So these look fairly complex right, for the developer to worry about, but these are exactly the kind of decisions that the optimizer makes for you, provided it knows enough to be able to gauge whether A is small, B is small, etc. So let's just spend another few more minutes talking about partitioning. How do you even specify this, right? Remember we said partitioning, you partition A and B to arrive at this partition hash join approach, etc. How do you specify it? There are two methods to do it. One, at the time of creating the table, which is what I call as permanent partitioning of a table, and the other is at the time of specifying a query. So that's more temporary, right? It's query time partitioning. So the query time partitioning is done by using a specific set of keywords called as distribute by, and here you could you could use an expression which is like a function of the columns that you want to distribute by. But in most cases, most examples will just directly use the columns themselves, right? Either the key column or the surrogate key columns in concatenation, one of two. Yeah, so you could look it up from the Spark documentation. Effectively, what you're doing here is saying select statements, right? Select star from A comma B in a join A dot B equals B dot B, distribute by, and then say for the columns that you're projecting out, which is the columns in the select class, which column you want to distribute the answers by. And then that data frame then becomes, as a result, partition based on the columns you specify the distribute by class. That's query time partitioning. The permanent partitioning for table, you could create at the point of creation of a table. You could create it using the partition to by syntax even before the table gets populated. Like for instance, you could say create table, table 1 partition by key, semicolon, right? And that way the table gets created as a partition table. Then from that point on, if you start loading it with data, it automatically adheres to the partition specification that you've applied on it. Alternatively, you can obviously do the partition by as a clause at the point of creating the table and populating the table. So if you use a create table as select formulation, you could also do the same partition by clause as part of the table creation. So these partitioning concepts can be specified at the point of querying, like I mentioned. You could also ask the Planet Optimizer, especially in SparkSQL, to use one of these join types. Like you could say, use broadcast hash join, or use nested loops, use blah blah blah, right? But that has an impact. So the way you would do it is, of course, using some standard interfaces that the SparkSQL itself provides. In this case, it's called as hints. Other databases also provide hints, rather provide mechanisms of giving hints where the developer can actually tell the engine, by the way, you might want to use this specific algorithm for it, right? In effect, you are bypassing the declarative nature of SQL and getting into the how part of the execution, which is why I would not recommend it, because it becomes very quickly very complex to manage the moment you start specifying how, right? And the way the hints are syntactically expressed, while on surface it looks as though it's readable, the moment you start to build up a big body of code, it starts to become very, very unwieldy to understand. why did the performance of this thing fail yesterday in production? So the best practice is in fact you should leverage the cost-based optimizer and features like adaptive query execution that's there in SparkSQL and use that to your advantage. So remember we spoke about stats, we spoke about rule model, cost model, and those play a role in determining if A is small, etc., right? So all of that is what's the role of cost-based optimizer, and the specific functionality that SparkSQL also has, which is called as adaptive query execution. So leverage that, and that's going to stand you in better stead than going down the road of hints. I'll spend a lot of time on CVO in the next video.